Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
10 states that example 1 uses a similar approach to that needed in this problem. If you haven't looked at example 1 in this chapter, it just thermodynamics of change in temperature based on observed dose. I recommend going through that problem before looking at this here. Assuming you have, this time the temperature remains constant while a phase change occurs. So a sample of liquid water at 100 degrees Celsius and 1 atm pressure boils to a steam at 100 degrees Celsius because it is irradiated with a large dose of ionizing radiation. What is the observed dose of the radiation in rads? So we're not provided a lot here, but we do know that we can't just directly use the equation given for converting or absorbed energy based on the change in temperature, because our change in temperature is 0. All that we're experiencing is a phase change, right? So we're going from water to steam. So we go water to steam. And if we think back to our thermodynamics equation 12.5 in our textbook, states that this is vaporization such that the amount of energy produced in this reaction is given by m, the mass of the water, times the latent heat of vaporization given by LV. So this value in our textbook is given as 2260. Unit site is pulled out to be kilojoules per kilogram. So that means if we're in the scenario, because we have no temperature change, if we want to find the dose, we can rearrange equation 12.5 here. So dose obviously is just absorbed energy per mass to come to the dose, which would just be equivalent to this latent vaporization. So again, this term is specifically for water. So if we think we can rewrite our value here as 2260 times 10 to the 3 joules per kilogram, which gives us units of grays, which the question does specifically ask for dose in rads. So we know that in 1 gray, to get rid of grays, we divide by grays, multiply that by 100 rads. And simply we'll find that our final dose for this phase change is simply 2.26 times 10 to the 8 rad. And there you go. So this question does have a bit of a callback to chapter 12 and a little bit of chapter, I think, 15 as well. But this equation was first introduced in chapter 12, and using the units and values given to us, we can solve for this dose. So there you go.